So this project is about this Kemet vibration sensor right here. And I've collected a bunch of other instrumentation to try and help me analyze the sensor and try and figure out a bit about its performance and get a feel for how it works. So just going around the table here, we have some rulers which will help me create some vibrations. I think they may be too violent for the sensor, but we'll try them out. The meter, I might need that for troubleshooting some of the electronics. There's alcohol to run the Stirling engine over here, but those are later in the project. There's a plastic box and some foam, which I'm using to help with acoustics and vibration. Also a bottle for a resonant cavity. And most of the frequencies we're dealing with are audio frequencies, but we're talking about the vibrations in those frequencies. However, I'm going to play them through the speaker here so that we can hear them as well, to create more of a multimedia look at the data. And these are the components that came with the kit. So there's a Nucleo Cortex M7 beast of a microcontroller and a Bluetooth expansion module for it. I have a little microcontroller in the back here. I don't know if you can see it. But that one's going to monitor performance of the Stirling engine. There's a lighter over there. This little module here is a audio amplifier so that I can drive this speaker from various inputs. This little module here is an MP3 player. I have stored on this device some sound samples, music, and some tones, 100 hertz, 500 hertz, kilohertz, and so on. I've also stored some white noise and some pink noise, so I can play noise and hopefully record that vibration and then do a spectrum analysis on my scope over here. So this module is a microphone, which it's just a custom microphone amplifier module that I built, and it has a little electret microphone on it, and you can change the sensitivity of the microphone. This device is a piezoelectric speaker. And I've just got it sitting on some foam right now. This device is a driver for audio surfaces, so this will turn any surface into a speaker, but it can obviously create vibrations that will vibrate a table, and I'll try and use that to see how that affects the vibration sensor. I have a breadboard which I'm using to connect a bunch of things together. This power supply has 3 power supplies. One on the left is 5 volts, which I'm using to power the microphone. The one in the middle is 8 volts. I'm using that to power the audio amplifier. And the one on the right, the blue one, is 3.3 volts, which I'm using to drive this vibration sensor. And of course the oscilloscope will be used to monitor the vibration and the microphone at the same time. So on the top trace here, the blue trace is the vibration sensor, and the yellow trace is the microphone. And you can see here, this is some music that I just recorded, and it obviously has a really good correlation between what the vibration sensor is seeing and what the microphone is seeing. However, of course, they don't see the same thing. as we'll show when we do some experiments. But that's an introduction to most of the equipment that I've collected so far. And next up, we'll just try a few things and just start to get a feel for how this vibration sensor works. Okay, the first test I'm going to do is just play some music. It'll be an interesting test. So you can see I have right now the microphone on this yellow trace, and it's picking up my voice quite well from all the way over here. But the vibration sensor on the blue trace is not picking up at all, which is fine because I'm not vibrating it. But if I play some music, if I put this vibration sensor right on this little speaker here, it's not really making good contact right now, but nonetheless it will vibrate as that speaker vibrates, just for a quick test. So if I start playing it, you probably can't hear that too well, so I'm going to put this box on top. And my microphone in there. So you can probably hear that. So you can hear that, and you can see it on the screen as well. Although the microphone is picking up my voice as well as the speaker, so it's only when I'm not talking that they will be the same. So that's a quick test to show that the microphone and the vibration sensor are both picking up what's coming out of this piezoelectric speaker. Now I'm going to drive this speaker with a bunch of different signals and see how the vibration sensor and the microphone, for that matter, respond. So I'm going to try some tones, different tones, and I'm going to try sweeping the frequency from 10 hertz all the way up to 20 kilohertz, just to see what the amplitude is at each frequency. And I'm going to try sending some white noise and some pink noise in there, and trying to get a plot of the frequency response of the device. Now, of course, some of the frequency response will be due to the speaker characteristics, the microphone characteristics, and of course the vibration sensor characteristics. But we will explore and see what they look like. One thing I didn't point out before is this little box here. It's full of special wax, which will allow me to mount the vibration sensor with good mechanical coupling to whatever it's measuring the vibration of. And eventually it will be measuring the vibration of this Stirling engine over here. Another thing which probably isn't too obvious is I have the output from the oscilloscope connected here, and I'm going to be able to run that through the audio amplifier to the speaker, or to this speaker, and this oscilloscope can generate waveforms, and it can do things like triangle waves, square waves, sine waves, and it can sweep the frequency. So it can do complicated waveform generation, and that's going to help me characterize the performance of this sensor. Another thing that this oscilloscope can do is, of course, it can capture the waveform from the vibration sensor or the microphone, and then it can actually replay it back out, so we can hear how faithfully the sensor captured the sound. So we can play some music through the vibration sensor and then play it back through the speaker to see if it came back reasonably close to the original. And of course there's distortion in the speakers, and both speakers and the microphones and so on, but we will see how close we get. So it's taken a while to get all these connectors soldered on and in the right sex and so on to make these connections happen in the way I want to do my tests. But I think I've got enough together now to actually start doing some real tests. And so stay tuned.